Okay, here I am going to say good morning today because I am taping this lecture in the morning. Usually I tape in the afternoon, so there is a little bit of a change here. Okay, so this is our 40th lecture, and the lecture series is supposed to run to about 40 lectures, but I might go 1 or 2 lectures over just to make sure that I complete the material. So the title of today's lecture is a transform approach to cyclic codes. So what that means is that we worked very hard in trying to understand finite fields, because that is the mathematical background you need to be able to understand cyclic codes, and now finally we have reached that point where we are ready to start studying the codes themselves. Okay. But as usual, I will begin with a quick overview of what we discussed last time. So, here is our lecture from last time, and the first thing that we actually did was we completed our discussion on the minimal polynomial, where we showed that the minimal polynomial has degree, where we discussed the degree of the minimal polynomial and noticed that it has degree m only when it is the minimal polynomial of a primitive element. So, let me, as I do this, let me put down the summary. So, we completed our discussion. Then the next topic that we moved on to on finite fields. So, we did a little bit of jumping around in the last lecture. We talked about subfields of a finite field, that is, and this picture over here gives you an excellent overview. It tells you that the subfield structure is completely determined by this exponent over here. So, here you have 2 to the 12, and so the subfields that it contains are of the form 2 to the m, where m divides 12. And the other thing that we did was, along as an aside, we also discussed a useful lemma which says that if you take x plus y and raise it to the pth power, you get x to the p plus y to the p. Okay. So, let me say subfield structure, then we did this lemma, then we also tested carried out a test for membership in a subfield, which is that for example, if theta to the p to the d is theta, then it belongs to f p to the d. Okay. All right. And then I sketched very briefly the proof that finite fields of every size p to the m exist for every prime p and every m greater than or equal to 1. And what I did was, because I wanted to make sure that I do not get bogged down in discussing finite fields, I put the detailed proofs in the appendix. So, as you go through your notes, please look through the notes. You will find that whatever theorem we have stated here is again stated in the appendix and followed by a complete proof. Then I actually stated a useful lemma, a theorem which says that if you take if you are looking at a particular finite field x to the p to the m, then the polynomial x to the p to the m minus x factors into the product of irreducible polynomials whose degree divides m. So, we will put that down also. So, that was our next observation. Then after that we showed that any two finite fields of the same size are isomorphic. So, what isomorphic means is that basically the two fields are the same, except that what you call one element here may be different. For example, you might call an element beta here, and in the other field it might appear as alpha cubed, but provided you recognize that beta is the same as alpha cubed and you follow through, then you will find that the fields are exactly the same, they add in the same way, they multiply in the same way. Okay. So, I will put that down. Then after that we discussed the add one table of a finite field, and what the add one table allows you to do, it basically allows you to work with the elements with the representation of the elements of the finite field in exponent form. So, you can regard the finite field as powers of some primitive element alpha and just learn how to add and multiply in that domain, and that makes it much easier. Okay. So, we also discussed the add one table. Then we talked about cyclotomic cosets, and so I introduced the definition of cyclotomic cosets, and I think that it is best illustrated by this example here. So, these are the two cyclotomic cosets mod 15. So, basically anything in which A is 2 to the some power times B, then they are equivalent. So, 1, 2, 4, 8, 16 mod 15 is back to 1. So, these are the cyclotomic cosets. They are basically equivalence classes under the equivalence corresponding equivalence relationship. And then we also talked about coset leaders. The smallest element in a cyclotomic coset is called the coset leader. Then there is a theorem, and we will not actually prove it here, which says that the minimum polynomial of an element beta is precisely the product of all linear factors of the form x minus beta to the p to the L, where L goes from 0 to d minus 1. So, what is this d? Basically what this d here is that d is the smallest integer such that beta to the p to the d is beta. That is, f the finite field of size p to the d is the smallest subfield in f p to the m, of which beta is an element. Okay. Proof is in the appendix. So, let us put that down. And the powers of beta of the form beta to the p to the L are called the conjugates of beta. So, what this theorem also tells us is that the conjugates of beta also share the same minimal polynomial, because they are zeros of the same polynomial. And after this you have the appendix. Okay, so, that basically was the last lecture. So, now getting back, so that I guess concludes our summary. I did want to break up the previous lecture into points, since it was a rather lengthy lecture. So, now let us move on to today's lecture, and here our interest is really in cyclic codes. So, remember right in the beginning we talked about block codes. So, our interest is back in block codes, except that we are interested in a particular class of block code known as cyclic codes, and we will actually give a formal definition soon. And the codes now are no longer binary, that they are codes over the finite field of size q, where q is a power of p. And there is an additional condition that comes about just because without this the theory will become much harder. Okay. So, this is for the purposes of tractability. You also require that q and n be relatively prime. So, our first goal, and the reason for this will become clearer a little later, is to find the smallest field. So, you are starting off with a finite field f q. Okay. So, that is the field over which you want to build your code. So, it is not, if it is binary, q would be equal to 2, but it may not be binary. For example, with the class of Reed-Solomon codes, those codes are not binary, and in fact the non-binary nature of those codes gives them their strength. Okay. So, this let us say is the alphabet over which you want to build your code for whatever reason. We will call this the ground field. Now, it turns out that in order to develop the theory of cyclic codes, what you need is a rather peculiar condition, that is, you need an element alpha whose multiplicative order is n, that is the smallest power of alpha which gives you 1 should be n. Now, it could be that this field itself contains such an element alpha, but often that is not the case, in which case what you can do is you can actually start with a smaller field and you can build up to a larger field. You can go up from here to here and you can be sure that there is a larger field that contains this field, which contains the desired element alpha. Okay. So, that is our goal, is to find this bigger field, and the way you find it is quite easy, because what you do is you say, okay, wait a minute, what I can do is I can take 1 q, q squared, q cubed, q to the k, q to the l, and keep going, and I do this modulo n. For example, if q was 2, then I would have 1, 2, 4, 8 and so on, and I would do this modulo n. If n was 15, I would go 1, 2, 4, 8 and then stop. Okay. But in general I will just keep going. Now, since there are only n residues modulo n, at some point this series must repeat, right, 2 elements must be the same modulo n. Okay. So, perhaps I should emphasize that and write this is true modulo n. Okay. Some 2 powers must agree. Now, without loss of generality, we can assume that L is greater than k. So, that is equivalent to saying that q to the L minus k is equal to 1. Again this is mod n. Okay. So, then now that we know this, it is meaningful to ask the question, well, what is the smallest power of q such that q to the m is equal to 1 mod n. Okay. Once you found the smallest integer m, then that particular m is called the multiplicative order of q mod n. Okay. Okay, it sounds a little bit mysterious. Why would you keep doing this? The reason is the focus is on this equation over here. This equation is key, because what you really are going to do is you are going to exploit this equation. What this, remember, our hunt is for this element alpha whose multiplicative order is n. See, that is what we are actually hunting for. And what we have here is this expression. Okay. But this expression is telling us that n divides q to the m minus 1, and that is important because it tells us that in the finite field f q to the m, and we know that finite fields of every size of this type exist, because q itself is some power of a prime. So, q to the m is also some power of a prime, and therefore, a finite field of this size exists. So, in this finite field contains an element of order n. Why is that? Well, because let us say that there is let beta be a primitive element of this finite field, then the order of beta is q minus 1. So, if you raise beta to the power q minus 1 by n, then this element alpha will actually have order n. Okay. So, that is the reason for actually working this hard. So, again, just to quickly recap, our goal was you want to build cyclic codes over this field which we call the ground field, but it turns out that in order to develop the theory you need the presence of an element alpha whose multiplicative order is n. So, you are forced to enlarge the size of your field and go to a bigger field which contains the element that you are actually looking for. all right. So, let us keep going. Example, for example, when q is 2, n is 15, then the smallest power of 2 which will give you 1 mod 15 is 4, because 2 to the 4 is 16, which is 1 mod 15. And here it turns out that you can simply you need an element of order 15, but the primitive element in f 2 to the 4 is itself of order 15. Okay, so there that does it for you. The second example, which often crops up with Reed-Solomon codes, is that q is a power of p and n is q minus 1. Note that the condition that n and q are relatively prime is satisfied, in which case you are looking for the smallest power of q which is equal to 1 mod n, but since q is n plus 1, that is just m equal to 1. In this case, you do not need to enlarge your field, and you can find the element alpha that you are looking for within the ground field itself, and you can choose alpha to be beta, where beta is any primitive element of the ground field. Okay. So, this situation is characteristic of Reed-Solomon codes, whereas this is characteristic of BCH codes. Okay. Okay. Now we are actually going to discuss, and perhaps it is worth highlighting this. So, I will write finite field transform. Okay, so, we are beginning a new topic, finite field transform. Okay. So, what in respect to this topic, what our previous topic was all about was actually trying to find that element alpha, because in constructing the transform we will need this alpha. So, here is the definition of a finite field transform. Let q and n be relatively prime. Let m be the multiplicative order of q mod n. Let alpha be an element of order n in fq. Let at, t goes from 0 to n minus 1, be a vector of length n over fq to the m. Okay. Then if you set a hat of lambda, so you look at this expression over here, this is called the finite field transform of a of t. Now, if you look at this and think about it, there is a lot of resemblance with the discrete Fourier transform, okay, but I leave it to you to make that connection. Also this element that we were looking for alpha appears here. Okay. So, then the finite field transform is defined according to this expression. Okay, so, this is the finite field transform, and so we will be working with this expression many times in the course of this lecture, and analogous to the way you develop properties of the discrete Fourier transform or the Fourier transform or the Laplace transform or the Z transform, let us look at some properties that this transform enjoys. The first property is that of linearity. What do we mean by that? We mean that if you take the vector a sub t and let us say that it has transform a hat, and if b t has transform b hat of lambda, then if you take a t plus theta times b t, what is theta? Well, your a and b, now in this discussion a and b all belong to the larger field. Okay. There is a ground field and there is a big field, the ground field being f q, the big field being f q to the m. Here all our discussion is about the big field f q to the m. So, if a of t and b of t are sequences in the big field and theta also belongs to that big field, then the transform of this sequence here, which is a linear combination of a and b, has this transform. that is A t is replaced by A hat of lambda, B t by B hat lambda. So, that is linearity, and this is easy to prove. Okay. So, I will just leave this to you to show as an exercise. It is straightforward. So, it's a simple exercise. Another property, and this property is important because after all our discussion is about cyclic codes. So, now we want to understand how the finite field transform behaves under cyclic shifts, meaning that supposing you have a sequence A of t and you are aware of its transform, which is A hat lambda, and now you construct a second sequence B t, which is a cyclic shift of A of t by tau. That is, the tth element here is the t minus tauth element of A. Now, one point to note here is that when you subtract t minus tau, you are doing this modulo n. Okay, so, that is important. That it is because without this modulo n, it would simply be a shift. Okay, but because it is mod n, it is called a cyclic shift. So, in the sequel, now from now onwards, whenever we do arithmetic in the subscripts, okay, so we might say 2t or 3t or t minus tau or t1 plus t2 in the subscripts, the subscript arithmetic will always be modulo n. Okay. In the sequel, we will always assume that a subscript of A of either A or A hat, that the arithmetic is always computed mod n, and we will simply write A of t minus tau in place of this more cumbersome expression. Okay. All right. So, now let us see what happens when we have a cyclic shift. So, when you take a cyclic shift and you take its transform, so now what I have done is I have replaced B t by A t minus tau. Okay. Now, I am going to break this up into lambda t minus tau and lambda tau. I am going to pull this out because it is not a function of t, and then I have this expression here, and I got from here to here simply by replacing t minus tau by s, and again this is mod n. Reason being that alpha is an element of order n, so all exponent arithmetic is naturally mod n. Now, t ranges from 0 to n minus 1, and it is not hard to see that as t ranges over 0 to n minus 1, so does s for any fixed value of tau, because you are doing arithmetic mod n. So, change of variables, you have this. Okay. And now, if you look at this, this is nothing but the expression for A hat of lambda. And so, that tells you that if A of t has transform A hat lambda, then its cyclic shift has transform alpha to the lambda tau times A hat lambda. And this is very similar to the expression that you have in the case of the discrete Fourier transform. There it is probably something like e to the minus j 2 pi f tau times A hat of f, but it is the same kind of a relationship here. One other point to note is that in our definition of the transform, we use a plus sign. We use a plus sign here, whereas with Fourier Laplace transforms you typically encounter a negative sign, but of course that is not a problem. As long as you are consistent, that works just as fine. Okay. It would work fine even if you defined your discrete Fourier transform that way. It is just a matter of convention. So, here we choose to use the positive sign. Then there is an inversion formula, as you might expect. If you can go from the time domain to the frequency domain, you would expect that you should be able to come back, and that is what the inversion formula tells you, that you can invert the expression A t by computing this expression over here. Okay. So, this is very similar to the way you would compute it in the case of the discrete Fourier transform. Now, I have given a proof over here, but the proof is straightforward. It is completely analogous to the discrete Fourier transform, and in this proof you use the fact that alpha has multiplicative order n, because if alpha did not have that property, this proof would not work. Okay. But having said that, I think I am going to skip this proof so that we can keep our momentum. Okay. So, the inversion formula very similar to the case of the discrete Fourier transform, that is that where you had a plus in the forward transform you have a minus now, and then you have an additional scale factor. Now, this n inverse is really, you should interpret this as the inverse of n in the finite field f q to the m. All right. Then there is also a convolution relationship, again completely analogous to the way it is with the discrete Fourier transform. If a of t has transform a hat lambda and b of t has transform b hat lambda, then if you take the convolution of these two sequences, and the convolution is given by this expression. Now, once again when I write, this is a cyclic convolution because this t minus tau is interpreted modulo n. So, perhaps I should may emphasize that. So, let us do that. So, let us write cyclic. So, cyclic convolution. So, under cyclic convolution what happens is that the transform of the result is nothing but the product of the individual transforms, and again completely analogous to the discrete Fourier transform case. So, I have left the proof as an exercise. So, we have gone through 4 properties so far. We have seen linearity, we have seen cyclic shifts, we have seen the inversion formula, and we have looked at convolution. Then there is another property, that of conjugacy. Now, conjugacy is really something that you already encountered before in connection with the discrete Fourier transform, except that it looks a little different. Basically what conjugacy is saying is that, look, when you take the discrete Fourier transform, you are taking you can take the transform of complex signals just as easily as you can take the transform of a real signal, right, because even though your signal may be real, the discrete Fourier transform will be a complex waveform. But for the particular case when the function itself is real, then the transform domain, the transform of a real signal satisfies a certain conjugacy property, namely something to the effect that f star of f is f of minus f. Okay, so, there is a certain relationship in the transform domain that comes about because your time domain signal happens to be real. So, exactly the same thing happens here, meaning that up to now we have been working entirely in this field which I have called the big field, that is your vector a t, all the symbols were in the big field, that transform a hat lambda, all the symbols were in the big field. But now we are going to actually investigate, well, what happens if actually my original signal a t had symbols in here. And in fact, in practice that is the case we are going to consider, because our interest is primarily in cyclic codes where the alphabet is f q, as I mentioned earlier, right. So, you are really interested in here, you are forced to work with this big field simply because you would not be able to take transforms in this field simply because you do not have an element of order n in the ground field, you have to go to a bigger field. And so, what happens then? So, supposing a of t belongs to f q for all t, that is this sequence lies entirely in the ground field, what can we say about the transform? So, that is the conjugacy relationship. It turns out that in this case the conjugacy that results is this, that if you look at the transform a hat evaluated at lambda q, then that is the same as a hat lambda, but raised to the power q. Again, lambda q is a computation that you are doing in the subscript, and as I have pointed out, either with the sequence or its transform, whenever you do arithmetic in the subscript, this is computed modulo n. Okay. And it turns out that, so what this is saying is that if my sequence lies entirely in the ground field, then the transform satisfies this conjugacy constraint. But the converse is also true, namely that if I have a sequence whose transform satisfies this conjugacy constraint, then that sequence must actually be in the ground field. Now, before proceeding further, I have a couple of slides which say, I keep saying that the subscript arithmetic is modulo n, and there is an alternative way of thinking about it which might make it easier to picture, and that is that you think of all your sequences A t. Now, up to now we have thought of A of t, for example, as a vector whose length is n. Same thing with the transform, but you can instead think of these as periodic sequences. So, this is the alternate picture, that is, you think of your sequence as being periodic with period n. Okay. Then it is automatic that all subscripts are computed modulo, all subscript arithmetic is modulo n, because this is really the nth term in the sequence. But since a n is a 0, that is the same as computing the subscripts mod n. Okay. So, this is the other way to think about it, that is, that really although you are working with only a fragment of the sequence, that fragment has all the information because it is one complete period of the sequence. Same thing in the transform domain. Now, you might say, well, do not I have to worry about consistency here? Well, you do not, because here is the definition of the transform, and if this is periodic, you are wondering, is this periodic? But you can check, because if you add n to this, then you will be adding n to that, and since alpha has order n, you will find out that a hat of lambda plus n is the same as a hat of lambda. Okay. So, maybe I should just add so let me reword this slightly. Since alpha has order n. All right. Okay. So, with that, now let us get back to our conjugacy relationship. So, remember that what we are trying to actually say is prove that if A of t lies completely in the ground field, that in the frequency domain, in the transform domain, you have this conjugacy relation. So, let me formally call this the conjugacy relation. All right. So, we want to prove this, and so this is quite straightforward. So, let us start with this expression and we will reduce it to this form. So, a hat lambda q, you just follow along with the definition. So, in place of lambda we have lambda q, but then you can regard this as a alpha to the lambda t raised to the qth power, and also recognizing that a t, remember a t belongs to the ground field, and a t to the q is therefore a t, okay, because this is the test for membership in a subfield, if you remember, that a t belongs to the subfield f q if and only if it satisfies the property that a t to the q is a t. So, we did this in the last lecture, and we reviewed that today. So, that means that you can take this replace this by a t to the q, and therefore regard this whole thing as being raised to the qth power. And since q is a part of the characteristic, you can take this q completely outside the summation, but what is left inside is nothing but a hat lambda. Okay. So, that proves that a hat of lambda q is a hat lambda raised to the qth power. Now, for the converse. So, the converse tells you, well, supposing the conjugacy constraint holds, then am I assured that the sequence belongs to the ground field, and the answer is yes. Okay. But again, I think I will just let you read through it on your own. in the interests of making up some time. Basically, the way you show that this implies that the sequence is in the ground field is to apply the membership test. So, what you try to do is show that A sub t to the q is A sub t again, and so this is your starting point, and then after some massaging you can actually bring it to the point of A sub t, which proves that it is in the ground field. Okay. So, the important thing to keep in mind here is that a sequence A of t is in the ground field if and only if its transform A hat of lambda satisfies the conjugacy relationship that is given here. All right. Okay, so now we are ready to talk about cyclic codes. Okay, so this was our goal, and I think that everybody listening to these lectures has been remarkably patient, but that is the way it goes. The big barrier to understanding cyclic codes is finite fields, and we have just gone through finite fields. So, now you are ready to actually discuss this, and with the requisite background in finite fields, the theory actually is quite straightforward. So, first of all, what do we mean by cyclic codes? So, of course, we are talking about cyclic error correcting codes, and these are block codes. The other thing which is not apparent from the name is that this code is a linear code. So, people talk about cyclic codes all the time. At the back of their mind, they really mean linear cyclic codes, but since cyclic codes are almost invariably linear in practice, people just I guess sort of laziness just call them cyclic codes. Okay, so, you should understand, and we will do the same in this class. We will assume that cyclic codes is a reference to linear cyclic codes. Okay. So, what is the definition? Just take a sip of water here. So, a linear cyclic code of block length n is a collection of n tuples such that two properties hold. One is, of course, it must be a linear code. So, you must satisfy the linearity constraint, which says that if C t superscript 1, C t superscript 2. Okay, so, let me just correct that, that should have been a ordinary 2, Arabic numeral 2. So, if C t 1 and C t 2 are two code words, then their linear combination must also be a code word. Okay. Must also belong to the code. Right. So, if each of these is a code word, then their linear combination is also a code word. This theta here belongs to f q. So, now our codes are over the ground field. So, linearity involves scaling by elements in the ground field, and if you just think about it, what you are really checking is that C is a vector space over f q. In fact, it is a subspace of f q to the n, and this is nothing but the subspace test. Okay. So, that is the first condition that you need to meet, that is, it is the linearity condition. The second condition that you need to meet is one of cyclic shifts. You need to verify that if C of t is a code word, then every cyclic shift. Okay, so, cyclic shift is kind of like a wraparound shift, is also a code word. So, here in this code word, when you put t equal to 0, you get C of minus tau, but since arithmetic is mod n, that is C of n minus tau. Okay. Or if you think about it as a periodic sequence, you will come to the same conclusion. Okay. So, what we require is that if this code word belongs to the code, then every wraparound cyclic shift, wraparound shift of this code word also belongs to the code. That is, the code is closed under cyclic shifts. Okay. So, that is the definition of a cyclic code, and now what we will do is we will go ahead and analyze these codes, and it turns out that a very convenient means of analyzing them is using these finite field transforms. My own exposure to this viewpoint came many years ago from a noted coding theorist, Lloyd Welch. Nowadays it's the other proponent of this viewpoint is Richard Blehut, and you can find this discussed in his textbooks on coding theory. Okay. All right. Now, given a code word CT, we define. So now now I am going to specialize our transform theory to the case of cyclic codes. So given a code word in a cyclic code, we define the transform of CFT in this way. Okay, so it's the usual definition, where alpha has order n in fq to the m, in which m is the multiplicative order of q mod n. Okay, so there is nothing new here. We already understand how transforms are defined. We understand that if your sequence is in fq, in order to find an element of order n, you have to go to a larger field fq to the m. So we are completely familiar with all of this. Yeah, so this is just saying something that's obvious, that is, while the code symbols belong to the ground field, the transform coefficients in general lie in the big field. Now, in this context, we will regard C hat of lambda as the transform coefficient. Okay, so I guess I need to rewrite this a little bit. Is the transform coefficient of C of t at frequency lambda. Let me try moving this one last time. There we go. Okay. So it's the transform coefficient of this at frequency lambda. So we are going to interpret these subscripts of C hat as frequencies in the ordinary way you would do with the discrete Fourier transform. Now, it turns out that it's convenient. So we discussed cyclotomic cosets in connection with a finite field. So there is something, there are cyclotomic cosets that also show up here. They are slightly different in terms of their parameters, but the definition is more or less the same. So in this connection, what we do is we define two frequencies to be equivalent, okay, lying between 0 and n minus 1. If lambda 2 is lambda 1 times some power of q, okay, and again this arithmetic is computed modulo n. This can be verified to be an equivalence relationship, and in just the way I remember when we discussed the p cyclotomic cosets mod p to the m minus 1, there I wrote down the three I had three lines which actually showed that the reflexive, the symmetric and the transitive properties were satisfied. You can, in exactly the same way, you can verify that those three properties are satisfied here as well. So what that means is that this is an equivalence relationship, and a key property of equivalence relationship is that it partitions the set of all frequencies. So you think of the lambdas as being frequencies. So it says that the frequency domain is now partitioned into equivalence classes. Each of these equivalence classes is called now a cyclotomic coset. Okay, so the corresponding equivalence classes are called the Q cyclotomic cosets mod n. Here is an example. So supposing Q is 2 and n is 15. Okay, so this is going to be our favorite example, favorite set of parameters. then these you should think of these as now being frequencies. Okay. So, these all of these should now be regarded as frequencies. These are the various frequencies lambda. And now we have an equivalence relationship in which, in this particular case, you define lambda 1 equivalent to lambda 2 if lambda 1 is equal to some power of 2 times lambda 1 times lambda 2 mod n. Okay. So, that is our equivalence relationship in this particular case, and if you work it out, you will see that these are the equivalence classes that you get. In this case, they also happen to be the p cyclotomic cosets mod p to the m minus 1, but when you introduce cyclotomic cosets in connection with finite fields, then you are always dealing with p cyclotomic cosets mod p to the m minus 1. With cyclic codes and the transform domain like this, you are a little bit more free to choose these parameters, because n need not be p to the m minus 1, although it is the case here. So, for example, n may have been in this particular instance 5, for example. It is perfectly okay for n to be 5. So, anyway, these are the 5 cyclotomic cosets, and the convention is that when you have a cyclotomic coset, the smallest element, okay, the smallest representative or the smallest element in each of the cyclotomic cosets is called the coset leaders. Okay. So, each row is a cyclotomic coset and the smallest element is the first, that is how it is conventionally written. So, these are the various coset leaders. Okay. So, that is just mentioned here. Then there is the obvious statement that if there are kappa cosets with ni elements in the ith coset, then the sum of the ni will give you n. So, for example, here this coset is of size n1 equals 1, n2 equals 4, n3 equals 4, n4 equals 2, n5 equals 4, and the sum of all of these is 15. Okay. That is just introducing some notation. Okay. So, just to quickly recap, what we have done so far is say, look, our interest is in cyclic codes. We defined what it means to talk about a cyclic code. We said that now we are going to apply our transform theory to the code words. That is, I am going to have a code word, I am going to treat that as my time sequence, and then I am going to compute its transform. Okay. And then in the transform domain, we are going to actually divide the frequencies into equivalence classes, which are called cyclotomic cosets. Now, the reason for doing that, or the motivation is because of the conjugacy constraint. Remember, we had the conjugacy constraint that if the code word belongs to the ground field, then the transform actually the transform values satisfy the conjugacy constraint, and that brings in lambda q given lambda. Okay. So, it turns out that that is the reason why we are interested in these cyclotomic cosets, but we will see a little bit more of this pretty soon. So, now we come to now we are slowly winding up our way to actually saying, look, I have given you a definition of cyclic codes, but in a sense I can give you a simpler definition of cyclic codes in the transform domain. So, that is where we are headed. Okay. So, a subset S of the integers from 0 to n minus 1 is said to be a closed set of frequencies, provided if lambda belongs to S, then q lambda must also belong to S. Okay. So, that means that these are you typically think of these as conjugates, lambda and q lambda. So, if lambda belongs to S, then q lambda must also belong to S. Now, you can actually verify that this forces closed sets to be the union of cyclotomic cosets. Why is that? Because let us go back to our example here. Supposing I was trying to construct a closed set and I happen to pick 3, and I said I want 3 to be in my closed set. But because the set is closed, I am forced to include 6, 12 and 9. Okay, so when I include 3, I am actually bringing along the entire cyclotomic coset. Supposing I next choose 2, I am forced to bring 1, 2, 4 and 8, because 2 times 2 is 4 times 2 is 8 times 2 mod 15 is 1. So, I am forced to bring along this entire cyclotomic coset. For this reason, closed sets are the union of cyclotomic cosets. Now, we come to a key concept, that of the null spectrum. The null spectrum is something that is associated with the cyclic code, and it turns out to characterize the cyclic code. So, let C be a linear cyclic code of block length n over the finite field of q elements. Then the collection of frequencies, so this ns here stands for the null spectrum, then the null spectrum of the code is the collection of all those frequencies lambda having the following property. Of course, since the code words are of length n or period n, if you think of them as periodic sequences, the lambdas lying between 0 and n minus 1. And now the requirement is that you take all those frequencies having the property that every code word in the code has a transform value of 0 at this frequency. So, that is why it is called the null spectrum. So, the null spectrum is the collection of all those frequencies where the transform value of every code word in your code is 0. Okay. So, that is called the null spectrum of a code. It turns out now that the null spectrum of a cyclic code is a closed set. In other words, you can actually construct cyclic codes very easily, because all that you need to do, it turns out, is, let us go back to our cosets here. So, supposing for instance I was designing a cyclic code here, and it turns out that you can actually design cyclic codes in a very simple way. Maybe what I will do is, let me just copy the page and insert it where I can use it. Okay, here we go. So, I will just edit this a little bit, some of this is unnecessary on this page. Okay, here we go. So, if I wanted to design a cyclic code here, as it turns out, then all that I need to do is specify a certain null spectrum. Now, you know that the null spectrum is a closed set, that is the set of all frequencies where all the code words have transform value 0. That is a closed set, we will show, and so I can design a cyclic code by just looking at each of these cosets and saying 0, not 0. Okay. So, for instance, I can design a cyclic code in here by just saying I am going to choose this 0, 0, and then I am going to put stars here, meaning that I am not going to impose the 0 value here. And then it turns out that the presence of these two zeros implies that this set over here is then the null spectrum of the code. And it turns out that designing a cyclic code is as easy as that. It is just picking a certain union of cyclotomic cosets and declaring that to be the null spectrum. And then the result is a cyclic code, and we will show that. Of course, the big question is, how good is your cyclic code? Okay. So, there you have to think a little bit more, and there is a certain result that simplifies the design of cyclic codes, a very simple result, and we will come to that. But the point I want to make is that the transform domain approach gives you this complete simplicity. I mean, it can't get any simpler than this, that you are saying that all that a cyclic code is just a collection of vectors whose transform values are zeros at a closed set, that is at every frequency in the union of a certain collection of cyclotomic cosets. So, that also means, for example, that if you are constructing cyclic codes which are binary, because q is 2 of length 15, then the total number of such cyclic codes is precisely 2 times 2 times 2 times 2 times 2, which is 32, because for every cyclotomic coset you can either choose to include it in the null spectrum or not. So, that gives you a binary choice, and there are 32 possible choices like that, and each one of them gives you a distinct cyclic code, and that completely describes all cyclic codes whose block length is 15 and whose alphabet is binary. Now, which are the good ones amongst those? Well, we will come to that. Okay. So, we have just about a minute left, and the first theorem, the first lemma result is that the null spectrum of a cyclic code is a closed set, and I have already mentioned this. Okay. So, we will begin our next lecture by actually proving this. So, I think that this might be a good place to stop now. Okay, thank you.